You've seen the incredible advances in multimodal AI models recently. It's amazing stuff.
Oh, absolutely. They can look at an image and, you know, whip up a creative story or scan a chart and actually nail complex math problems.
Right. They seem to be getting astonishingly good at connecting what they see with what they can say or calculate.
Mhm.
But it raises a big question, doesn't it? How well do these models truly think? Especially when the task needs them to combine visual information with complex logic and reasoning.
That's really the frontier researchers are pushing on right now in multimodal AI. It's like one thing for an AI to recognize a cat in a picture.
Sure, standard stuff almost now.
Yeah. But it's quite another for to look at a series of shapes and deduce the underlying rule
Yeah.
to predict the next one. That's different.
Absolutely. And that's exactly what this deep dive is all about today. We're taking a close look at how researchers are trying to rigorously measure something kind of tricky.
Very tricky.
The logical reasoning abilities of multimodal large language models, MLLMs, specifically when that reasoning has to happen by interpreting visual information.
Our main source for this is a really interesting research paper. It introduces a brand new benchmark designed specifically for this exact challenge. It's called Logic Vista.
Logic Vista, okay.
And we'll also touch briefly on another source that looks at different ways to generate data for training AI on these kinds of reasoning tasks.
Okay, so our mission today is to unpack these sources for you. We want to understand the unique challenges in evaluating AI on visual logic, really dig into the specifics of this new Logic Vista benchmark.
And crucially, find out what the results tell us about the actual reasoning capabilities and, maybe more importantly, the limitations of today's most advanced MLLMs.
All right, so let's jump into the core problem. What were the creators of Logic Vista trying to tackle? What was missing?
Well, we already have benchmarks, right? Lots of them test MLLMs on visual tasks.
Yeah, like object recognition or reading text and images. You hear about text VQA or VQA V2.
Exactly. And others, like, say, Raven or MMVet, they do involve visual elements for spatial or mathematical reasoning.
Right.
But the researchers found a gap. While logic might be involved sometimes in those tasks, there wasn't really a dedicated systematic way to evaluate explicit logical visual language reasoning.
Ah, okay, so that specific skill.
Right. Think about how we humans solve visual puzzles or understand complex diagrams that require inference. That specific cognitive skill wasn't being directly tested and measured in a focused way.
And they highlighted some specific issues with the existing methods, didn't they?
They did. Two main things, really. First, that lack of systematic testing for explicit visual logic skills we just mentioned. It's fundamental to how we navigate, solve problems, interpret things visually.
Makes sense.
But most AI logic tests have traditionally been text-based. The question was, can the AI see the pattern and apply a logical rule just from the visual input?
Right, like you can give a model text that says, all A are B, C is A, therefore C is B. Test its text logic. Fine.
But can it look at a visual sequence where the pattern isn't spelled out in words and figure out what comes next? That needs a different kind of integration.
And the second big problem they pointed out.
Oh, yes, potential data leakage. This is a big one in machine learning evaluation.
Explain that a bit.
So a lot of existing benchmarks use images and questions scraped from the public internet. Vast amounts of data.
Okay.
Well, if a model was trained on that huge data set, it might have accidentally seen the test questions or very similar examples during its training phase.
Oh, I see. So it's not reasoning, it's remembering.
Exactly. It doesn't truly test reasoning ability. It might just be testing memory or recognizing a pattern it already encountered. That's not a fair or accurate measure of genuine logical deduction or induction.
Yeah, it leaves you wondering if it's really figuring things out or just regurgitating something it saw online.
Precisely. So that's the context for Logic Vista. It was created specifically to fill this gap, focusing squarely on integrated logical reasoning within visual contexts.
And how did they tackle that data leakage problem?
Okay, this was clever. They took a really important step. The visual data and questions for Logic Vista come from licensed IQ test sources.
Ah, so not just scraped from the web.
Right. These are sources that are not freely available online. You'd typically need to pay or register to access them.
That makes a difference.
A big one. And they even went further, performing reverse image searches on samples to double-check they weren't easily findable. This whole effort was crucial to ensure data integrity.
So they could be more confident they were isolating and testing reasoning itself, not just prior exposure.
Exactly, making the test much more robust.
So what does Logic Vista actually contain?
It includes 448 multiple-choice questions. Every single one requires the AI to look at something visual and apply logic.
And they cover different types of logic.
Yes, 5 key categories, all presented visually. First, inductive reasoning.
Finding patterns, right.
Yep. Finding patterns, figuring out the general rule from specific examples, and then applying it. The paper shows examples like sequences of shapes changing inside a hexagon or patterns moving across grids. You have to look at what came before to deduce what comes next.
Okay, inductive. What else?
Then there's deductive reasoning,
Yep.
applying general rules or principles to specific visual scenarios. Think visual syllogisms or logic puzzles where there might be some text within the image that needs logical processing.
Got it.
Third, spatial reasoning. This is all about understanding relationships between objects in space.
Like rotations or fitting shapes together.
Exactly. How do shapes relate spatially? What happens if one rotates? How do pieces fit? That kind of thing.
Number 4.
Numerical reasoning. So, solving math problems, but the information is presented visually, often in charts, graphs, tables. The model has to interpret the visual data correctly before doing the math.
And the last one?
Mechanical reasoning. Understanding basic physics or mechanics presented visually, like figuring out which way gears will turn if they're connected, or how liquids might behave in certain containers.
Wow, okay. That's quite comprehensive. Covering different ways logic interacts with visuals.
And the questions also vary in how they present the info. Some are just diagrams. Some require reading text within the images using OCR, optical character recognition.
Ah, OCR.
And crucially, many tasks require combining both diagram interpretation and OCR, reading the text and understanding the picture together to solve the logic.
And you mentioned the creation process was thorough.
It sounds like it. The paper says it took about 4 months, involved multiple rounds of peer review independent checks, really rigorous.
Okay.
And importantly, they didn't just check the final answers. They also developed detailed human-written explanations for the reasoning process behind each correct answer.
That focus on the reasoning explanation itself seems key.
It's so important, right? It helps you understand how the AI is trying to solve it, not just if it stumbled upon the right multiple-choice letter.
Which leads us nicely to, what did Logic Vista actually show? What happened when they tested the big models?
Yeah, they tested 11 different state-of-the-art MLLMs, the ones making headlines, GPT-4o, Claude 3.5 Sonnet, Gemini Pro, plus some well-known open-source ones like Elavio, Mini-GPT-4.
And the results?
The big, clear finding. Logic Vista is tough, really.
Really? Even for the top models?
Yes. It proved to be a very challenging benchmark for all the models tested, even the best ones.
Can you give us some more detail on that? Where did they struggle most?
Well, looking at the detailed results, there was a noticeable pattern. Models performed significantly better on deductive and mechanical reasoning tasks.
Okay.
Compared to inductive, numerical, and especially spatial reasoning, those were much harder.
How much harder? Like, what kind of scores are we talking?
So for the best models, average scores might hit around, say, 65% on deductive tasks. But for those other categories, inductive, spatial, numerical scores often dipped below 30%, sometimes quite a bit lower.
Wow, below 30% on things like spatial reasoning for top models? That's surprisingly low.
It is, and this performance gap across different reasoning types is really fascinating.
Why the gap? Does the paper suggest why?
It does offer a compelling explanation. It likely comes down to how the visual parts of these models, the visual encoders, were primarily trained.
Oh, so?
They're usually trained heavily on standard computer vision tasks. Things like recognizing objects, that's a dog, that's a car, classifying whole images, or segmenting different parts of an image.
Okay, standard vision tasks.
And they're great at that. But those tasks don't necessarily teach the visual encoder to understand complex spatial relationships deeply, or to identify the kind of intricate inductive patterns needed for these logic puzzles.
Ah, I see. So the visual part might not be extracting or highlighting the specific logical information that the language part of the model needs to actually perform the reasoning task.
That's the hypothesis.
Yeah.
The visual model sees shapes, colors, objects, but maybe doesn't inherently grasp the rules governing their arrangement or transformation in the same way a system trained explicitly on logical patterns might.
That makes a lot of sense, actually. The training objective mismatch.
Exactly. And this brings us to another key insight from Logic Vista. The importance of evaluating not just the answer, but the reasoning.
Right. You mentioned they used 2 methods.
Yes. Standard multiple choice questions, or MCQ, where you just pick A, B, C, or D. And also open-ended chain of thought, COL to D, where the model has to explain its step-by-step reasoning to get to the answer.
And what did that comparison show?
Here's what's really revealing. Models consistently scored higher on the multiple-choice questions than they did when asked to explain their reasoning via chain of thought.
Interesting. Why would that be?
Well, the source suggests that MCQs might allow models to get the right answer sometimes through, well, educated guesses or maybe matching surface features or even just partial understanding combined with eliminating bad options.
Process of elimination or latching onto a superficial clue.
Precisely. But the chain of thought evaluation is like the acid test. It reveals whether the model genuinely understood the underlying logic.
And how did they do on that QT part?
Well, when models attempt QT on the harder Logic Vista problems, they often fail,
Yeah.
sometimes spectacularly.
How so?
They provide incorrect or nonsensical explanations. Or, maybe even worse, they hallucinate.
Hallucinate, like make things up.
Essentially, yes. They invent details or relationships that simply aren't present in the image, often to try and justify an incorrect answer they've reached.
Wow. Can you give an example of that?
Yeah, the source provides some really telling ones. There's a star pattern example. The model could identify the stars in boxes' basic shapes, but it completely missed the crucial spatial relationships and the simple numerical pattern rule that determined how many stars should be there. The core logic.
It saw the pieces, but not the puzzle logic.
Pretty much. Or another one with a sequence of triangles and circles. The model saw the shapes, but then it hallucinated that a circle was somehow splitting into two, completely misinterpreting the actual simpler sequential pattern.
Just invented a mechanism that wasn't there.
Exactly. And there's a sled example, too. The model could describe the sleds generally, but when asked about specific, intricate spatial details, like differences in runner width between sleds or relative sizes, it really struggled.
And hallucinated again?
And even hallucinated relationships to try and answer the question when pressed.
But they didn't fail at everything, right?
No, definitely not. They contrasted this with an example where a model did well, like describing some springs in an image.
Ah, so description is okay.
Right. That task is more about recognition and description, is identifying objects, their basic properties. It's less about complex spatial or inductive reasoning.
So this distinction really highlights that current models are still much stronger at recognizing and describing what they see.
Than they are at reasoning about intricate visual relationships or abstract patterns. That seems to be the core finding.
Did they find anything else interesting, like about model size?
Yeah, they did find a general correlation. Larger models tended to perform better on Logic Vista.
Okay, bigger is generally better.
Generally, yes. But it wasn't a strict linear rule. Some variations existed, suggesting that while scale helps, things like the specific model architecture and, crucially, the quality and type of training data used for both the visual and language parts are also really critical factors. It's not just about size.
Right, the details matter. And you mentioned another source briefly about generating data.
Just briefly, yes. It touched on another angle. Researchers are exploring this in Logic Source. Their effort focuses on synthesizing data specifically to train models on logical reasoning.
So creating artificial training examples.
Yeah, drawing concepts from various existing benchmarks, even logic elements from games like Minesweeper, to try and build better training sets specifically for reasoning skills. It just shows that the community is actively exploring multiple paths to improve this capability in AI.
Okay, so bringing this all together, why should this matter to you, listening right now? Why care if AI models struggle with visual logic puzzles from IQ tests?
Well, because these underlying abilities, interpreting visual patterns, understanding spatial relationships, applying logic to what you see, they're fundamental to so many real-world tasks we might want AI to help with.
Like what?
Think about understanding complex diagrams in technical manuals, or interpreting data visualizations in business reports, or even things like visual navigation for robots or autonomous vehicles.
Okay, those all rely on this kind of visual logical reasoning.
They absolutely do. So knowing where current MLLMs struggle with these foundational skills helps us set realistic expectations about their true capabilities right now.
And understand their limitations, especially as these powerful tools get integrated more and more into our daily lives and work.
Exactly. You need to know what they're good at and where they still fall short.
So ultimately, benchmarks like Logic Vista are really vital tools, aren't they, for tracking the real advances in multimodal AI?
Definitely. They cut through some of the hype and the impressive demos
Yeah.
and reveal that while MLLMs have made incredible strides in connecting vision and language, their ability to perform complex, integrated visual logical reasoning, especially that tricky spatial and inductive stuff, still has a significant way to go.
And that chain of thought finding is pretty sobering, too. The idea that what looks like a correct answer might sometimes be closer to a guess than actual understanding.
Right. It suggests the reasoning might sometimes be more superficial than deep comprehension.
Which leaves us with a final thought, maybe something for you to ponder. If even the best, most advanced MLLMs currently struggle to reliably reason about these carefully selected visual patterns from non-public tests, what does that really imply about the kinds of complex visual tasks we should or perhaps shouldn't trust them with today, especially in critical applications?
That's a huge question.
Yeah.
And maybe the follow-on is, what kind of visual data, what specific training approaches will it genuinely take to teach these models to move beyond just recognizing and describing and to start to truly think visually and logically?